like to thank the organizers for giving me this opportunity to talk here. This is the title of my talk, the Cosmological and Spherical Symmetric Static Solution in Born-Infeld Gravity. So this is basically the follow-up of the previous talk, where we will summarize our recent works from our group. So first I will talk about the 2+1 dimensional solutions in Eddington-inspired Born-Infeld gravity, and the details of this Eddington-inspired Born-Infeld just has been discussed by Soumya. And then I will discuss the Lorentzian, the possibility of having Lorentzian wormhole solution in EIBI gravity supported by ordinary matter. And this work has been done by Rajibul Sheikh from our group. Then I will discuss this spherically symmetric static solution in EIBI gravity coupled to Born-Infeld electrodynamics. And I will cover these things: general solution, their limiting cases, etc. And then I will discuss a different setup of Born-Infeld gravity, and I will talk about a reduced Born-Infeld gravity, a reduced form of FTAG theory from that different setup of Born-Infeld gravity, and I will talk about a cosmological implication. Finally, I will give you a glimpse of our current work, which is EIBI cosmology with scalar Born-Infeld matter. So first, let me give you a brief outline of the Eddington-inspired Born-Infeld gravity. Details has been already discussed. So this is the action, and this action is functional of two independent variables, metric and connection. So here the connection is not the Christoffel symbol. They are independent, and matter is coupled to the metric only, not the connection. And this is the structure, and this kind of structure is called the Born-Infeld structure. Here this parameter small lambda is a constant, and it is related to the theory parameter or main coupling parameter kappa, and the cosmological constant capital lambda in this way, small lambda equal to kappa capital lambda plus 1. Okay, and these are the field equations given here. So to describe the field equation, I introduce a auxiliary metric Q, which is defined as Q mu nu equal to G mu nu plus kappa R mu nu. And with this definition, if you vary this action independently with respect to the connection, you will get the metric compatibility condition for this auxiliary metric. So this will enable us to define the connection as the Christoffel symbol of the auxiliary metric, this one. So then if you vary the action independently with respect to the metric, then that will give you this field equation where you have this energy momentum tensor coming. And you can show using this field equations that this automatically lead to the conservation equation, usual conservation equation, where the covariant derivative is described in terms of the metric, physical metric G. Okay, so now let us go to the EIBI solution in 2+1 dimensional EIBI gravity. And our motivation in this work was to find some analytical and simple results. So for example, if you take a FRW line element in 2+1 dimension, then this one, where K corresponding to the usual flat, open or closed universe, and this FRW line element is coupled to the perfect fluid, where P is the pressure, rho is the energy density. And as Hans described that to solve to solve the field equation in this theory, EIBI theory, we have to assume also an answer for the auxiliary line element, which in this case I take like this, where if you look closely to this physical line element and the auxiliary line element, you will see the difference. Here U and V is coming extra.
Excuse me.
Yes.
Was there any special reason for going to 2+1?
Yeah, special reason is as I said, the motivation was because Soumya already told you that in 3+1 in cosmology we do not have the analytical solution. Numerically, we have to solve, even for dust in the universe. So that was the reason for that, whether we can have, so that then we can investigate with that line element what is happening clearly. So in this setup, so we have 5 unknowns, that is the scale factor A, U, V, pressure and density. And we have 4 equations from the field equation. 4 means 0, 0 and 1, 1 component of the 2 kind of field equation. One is the metric variation and another is the from the connection, the definition of the auxiliary metric. So from there you have 4 equations, and we have additional conservation equation, but conservation equation not the independent or unique, that comes from the field equation itself. So you have ultimately effectively 4 equations and 5 unknowns. So you need to another relation to solve this system of equation, and that is the equation of state. P equal to and I have taken here P equal to omega rho, the usual linear relation between P and rho. And this is a modified Friedman equation where H is the Hubble function, A dot by A, and on the right hand side we have G2 and F2 squared. So G2 and F2 both you can write it down in terms of rho after taking consideration of the equation of state. G2 and F2 you can write down in terms of rho, but U, V, everything can be written in terms of P and rho, and P is related to rho by the field, equation of state. So this is the solution. So for example, if you take the specially flat universe, K equal to 0 and cosmological constant lambda equal capital lambda 0, then for dust case you have the analytical solutions for kappa positive and kappa negative. You can see that for kappa positive the scale factor vanishes for a finite time, so that means there is a Big Bang like singularity. But for kappa negative the scale factor never goes to 0 for any time. So you have a minimum scale factor, so you have a bounce for kappa negative. But kappa positive you have singularity. So and in this is the plot for P equal to 0 case, and if you do the same exercise for P equal to rho by 2, you do not get the numerical solution even in 2 plus 1 dimension, but the numerical solution have the qualitatively the same feature as the P equal to 0 case, and that means you have singularity for kappa positive and bounce for kappa negative. And so therefore here the important difference from 3 plus 1 EI by cosmology is that in 3 plus 1 with any ordinary matter the cosmology is singularity free, there is no singularity. But in 2 plus 1 for kappa positive you have a singularity. So that's
kappa is entering in the denominator.
Yes.
Do you have proper kappa equal to 0 limit and connection to the Einstein result? It doesn't seem to.
Actually here kappa do not appear denominator. It is C1, that extra constant C1 and C2. It actually absorbs kappa. Means I have redefined the definition. Actually it comes like some constant which do not relate to kappa, and here kappa multiplied. So that's kind of.
The question is, when in the kappa tending to 0 limit.
Yes.
Do
That
you
should.
get T raised for 2/3?
Yes.
For
That thing will come. That thing will come. Okay. Now let us. So in this slide I will summarize. I will not giving the details of 2 plus 1 circularly symmetric static spacetimes coupled to perfect fluid, but I am summarized because I will discuss
Can you
in
see
more
the
detail.
Lewis slide?
Yes.
Can you see the Lewis slide?
Yes.
What happens when T is very small in the first equation? It becomes imaginary. AT becomes imaginary.
No. I will not take T.
Beyond
T is just a time parameter. So I will restrict T at that point when A becomes 0. The scale factor becomes 0. T starts from. I can rescale that.
Is that the beginning of?
Yes.
Yes, that is the beginning of the universe. That is it. So I will discuss many more spherically symmetric solutions later part. So I am just giving you the summary of this circularly symmetric static space-time means 2 plus 1 dimensional EIBI gravity. So for that we have assumed answers for the physical metric like this, and the answers for the auxiliary metric like this. The physical metric is coupled to the energy momentum tensor directly, and for this setup we have got the non-singular asymptotically antidecited spacetime of Lorentzian wormhole nature for negative kappa, when we have taken the equation of state P equal to lambda. That means inhomogeneous dust with lambda. If you take P equal to rho by 2 equation of state, then our result shows that though the radial distance RL, here this RL, radial distance RL goes to 0, we found that all the scalar invariants, that is Ricci scalar, Fresman scalar, all remain finite. So this is a non-singular spacetime, both kappa positive and negative. Okay, now I move to the next work by Rajiv Ulsek, which is to finding any possibility of finding a wormhole solution supported by ordinary matter in this EIBI gravity. So from Rai-Choudhury equation, it is known that near the wormhole throat, there is a violation of null energy condition, and in GR that directly relates to the violation of null energy condition, and that automatically leads to the violation of other weak and strong etc. energy conditions. So that means to support a wormhole solution in GR, you need exotic matter. But in some alternative or modified theory of gravity, it may be possible that violation of null convergence condition may not lead to the violation of null energy condition. And so let us try to, and in that case we may have the possibility to have a wormhole solution supported by ordinary matter. So let us look if there is any such solution in EIBI gravity. So the framework is like this. We assumed the physical element like this, where psi squared if R appears before dt squared, and there is a term dr squared by fr and r squared d omega squared. And for auxiliary line element, this is the answers for the auxiliary line element. The energy momentum tensor of anisotropic fluid has been taken into account by Rajiv, and that means the diagonal form of the energy momentum tensor will contain like this, where minus rho, alpha rho. So PR and P theta are different. And some author has shown in different paper that this energy momentum tensor can be obtained from a nonlinear electrodynamics theory, which the action for that is given here. So the energy conservation equation can be integrated to obtain a relation between the energy density is related to the r square or related to the r like this, where C0 is a constant and alpha is the constant which appears in the action. So for to satisfy all the energy condition, null energy, strong, weak, everything, you must have C0 greater than 0 and alpha is positive but less than or equal to 1. So if you take alpha equal to 1, this electrodynamics is reduces to the usual Maxwell's theory. So with this setup, the solution for kappa negative in the EIBI gravity will looks like this, where this is the line element for the physical metric, where psi has a form of like this, where R0 R0 is the minimum radial distance. So there is a minimum radial distance R0, which is related to the kappa and C0, the constants. The theory parameter kappa, C0 and alpha. And FR have the form like this. Now with this solution of the physical line element, Rajibul has computed the expansion, isotropic expansion, which is like this. So for at the R equal to R0, the expansion vanishes. So that means it is a wormhole throat. And also he has also checked that Rij, Ui, Uj, this is negative. For since alpha is equal to positive and less than 1, so it is negative. So the null convergence condition is satisfied. So that means it is a wormhole solution. Now another thing is that this for wormhole solution, psi squared phi r, that must be finite for all at the throat. So for that there must be a specific choice of the mass for which this condition is satisfied. Otherwise there will be divergence due to this term. And therefore the specific choice becomes the specific choice of mass becomes like this, where for alpha equal to half, this m becomes exactly 0. For alpha, any value other than the half have this value. And we can check that all the scalar quantities, the Ricci scalar, Tisman scalar, all invariant scalar quantities are finite at all r for such a specific choice of mass. And so that means the spacetime is regular. So we have a regular wormhole solution. Now for this specific choice of mass. Now if you take R0 squared, the minimum radial distance of the throat radius, that square is greater than mod kappa, then there will be existence of event horizon. That means that is a regular black hole solution. If you take R0 squared less than mod kappa, then there is a no event horizon, that means a wormhole solution. So R0 square equal to mod kappa, this is a critical value, and which distinguishes from the regular black hole solution and regular wormhole solution. And for that you can define a critical charge to mass ratio. For example, if you take the alpha equal to 1, that means the Maxwell's theory, this critical charge to mass ratio is equal to approximately 1.144. So that means if the charge to mass ratio is greater than the critical value, then you have wormhole solution. If you have charge to mass ratio less than the critical value, then this is a black hole solution, but the spacetime is regular. So we have seen that there is a possibility to have a class of wormhole solutions supported by ordinary matter in EIBI theory. Okay, now in this here now we discuss the EIBI gravity coupled to Born-Infeld electrodynamics, and we will see that we have obtained a class of spherically symmetric static solution, in this case which is new and interesting. So why I have taken Born-Infeld electrodynamics? Because in that way you invoke the Born-Infeld structure both in gravity and matter sector. So in the gravity sector you have kappa, and in the matter sector, say there is a another parameter b square. So which control the nonlinear effect in the gravity and matter sector respectively. So if you take kappa tending to zero limit, in that case your gravity sector reduces to zero, But if you take b square tending to infinity, that reduces to the Maxwell theory of electrodynamics in the matter sector. So we have considered the spherically symmetric and static case. That means the vector potential only contains the scalar field only, and electric field due to this localized charge for this case is given by this, where the term localized means the charge could be a point or it could be distributed over a spherical cell, and the right hand side of this equation contains the charge q, b, which is the parameter for the nonlinear effect in the electrodynamic theory, and u, v, nu, psi, these are the metric functions, where the metric is given here, the diagonal matrix form. And for this setup, the energy momentum tensor components are given by this. But the important point is that here is that the energy momentum tensor is not traceless, unlike the Maxwell's theory. So this is the solution in this case. The final line element physical for the physical space-time, which is this one, where u and v are the metric functions are given in this form. Here kappa b square appears in the metric function u and v, and to have the complete analytical form, you have to evaluate this integral in the e to the power 2 psi or e to the power minus 2 nu, this function which appears here, and m is the total mass of the charge. So the important point is that these expressions are analytical, and the space times are characterized fully by kappa and the parameter, nonlinear parameter for gravity and matter sector. Now in this slide I discuss the different limits of this theory. If you take q equal to 0, that means the vacuum, so that reduces to the Schwarzschild solution, because you already know that the vacuum solution in EI by theory is exactly same as in GR. If you take kappa tending to 0, that is the GR in the theory gravity sector, and b square tending to infinity, that means the Maxwell limit in the matter sector. In that case, you have a Reissner-Nordström solution. You recover Reissner-Nordström solution. If you take b square tending to infinity, then you have EI by solution with Maxwellian electric field, and these solutions are obtained by these authors and are analyzed by other authors in this paper. If you take kappa tending to 0, but b square is some finite value, that means you have a geonic black hole solution, this solution was obtained by this author. And here geonic black hole solution means the GR solution with Born-Infeld electric field. So in this figure, I have fixed the value of kappa, but I have varied the value of b square. That means I want to fixing the nonlinear parameter in the gravity sector, but in the matter sector I am changing the parameter and want to see the nonlinear effects in that. And we see that as you increase the nonlinear effects, that means as you increase the decrease the b square, the horizon radius increases. In the other case, in this figure, I have shown you the deviation from the GR sector, while I have fixed the value of b square, the nonlinear electrodynamics parameter, where this brown dashed line is correspond to the geonic black hole solution, and other is the deviation from that geonic black hole solution. And here we see that as you increase the nonlinear effect, the horizon radius actually decreases. We have also shown you shown the a very special case where b square equal to 1 over 4 kappa. For that, we have we got very simplified solution, which is this. So you can see that it is like a modified Dirichlet-Nordström solution, where 1 plus kappa q square by r to the power 4 terms appear here, and 1 plus kappa q square r to the power 4 times appear here. Here, while 1 minus kappa q square by r to the power 4 term appear before r square d omega square term. So if you put kappa equal to 0, you this solution exactly become to the Dirichlet-Nordström solution. And in this slide I have shown you the existence of horizon. For example, if you take the b square q equal to m, q equal to m thing, then you see that the existence of horizon depends upon the value of kappa. This shaded region corresponds to the black hole solution, but this white region corresponds to the naked singularity. So here we have also analyzed the photon propagation and deflection of light in this special case. So the important point is that photons no longer follow null geodesics in this nonlinear electrodynamic theory, because in the nonlinear electrodynamics theory you have a nonlinear wave equation, not the linear wave equation. So for that reason, photons no longer follow the null geodesics. And in strong gravitational field, this Born-Infeld kappa plays the important role. So the main point is that in this figure, here I have shown you the effective potential for this the b square equal to 1 over 4 kappa case, the special case in the just earlier slides, and you see that the photon sphere radius varies if you change the kappa value. If you fix the q by m ratio, charge to mass ratio, but still it depends upon the photon radius depends upon the value of kappa. So I just skip this slide. Okay, now let us now go to the different setup of this Born-Infeld gravity.
Do you get some constraint from his light beam?
No, we have just obtained, we have just analyzed the variation of this photon sphere radius, means how they vary with this kappa, how they are dependent upon the kappa value, the theory parameters that we have checked. And another thing we have done, that we have obtained the weak deflection formula, and where the smallest correction due to kappa becomes, and which is this one. So the smallest correction, the leading order correction due to the kappa value, it appears in the 1 over r to the power 4 term, because in the metric you see that the q square by r to the power 4 term is kappa q square by r to the power 4 terms appears in the metric. So therefore the leading order term appears here, r to the power 4. Alright. So now let us go to a different setup of Born-Infeld theory, which is a teleparallel version. So what is the teleparallel theory? Teleparallel theory means here the fundamental field is not the metric or the connection. Here the fundamental field is tetrad or Verben, which forms the orthonormal basis of the local Lorentz field, and the metric tensor is related to the tetrad field like this way, but this Latin indices refers to the local Lorentz field, and this Greek indices they refer to the general coordinate system. And we work not in the Riemannian connection or Riemannian space-time.
Riemann tensor is 0, no? It is gamma.
Gamma?
Tilde,
Yeah.
gamma tilde. Riemann tensor is 0.
R is 0.
Yes.
Oh, it is 0, you have written it.
Yeah.
So it's a flat space.
Yeah, flat space. This flat space in this connection. If you take this connection, then it is flat space. But here torsion is non-zero.
So So it's purely torsion. There is
Yes, purely torsion. There is no
gravity.
curvature. Curvatureless.
So torsion is a tensorial field. So you are just putting a field there. There is no gravity. T is a tensorial field. It transforms like a tensor. So you are
Yes.
just adding some symmetric field in the field theory. Am I wrong? Go on.
No, the effect of the gravity, it is like a gauge theoretic approach. Means it is not the metric theory. It is
There
not
no
the
gravity here
no.
because R is 0.
No, gravity is described through the torsion. That is the idea.
Gravity
Torsion is a tensorial field.
It is described through the torsion.
But torsion does not create any gravitation.
No, that's the whole point. That in these theories, they say that gravity is described, like you describe it in terms of metric, you will also be able to describe it in terms of torsion. That's the approach.
Not for this connection. Connection is 0 R.
R,
R-
there is
R-
no R here. R is
No,
not there at all.
excuse me, sir. Here you can calculate the R for the Riemannian connection.
Symmetric
also.
part.
Yeah. Then you will that is non-zero.
The
If you go back to the Riemannians,
Oh, your two
Okay.
connections.
yes, this is not the Levi-Civita connection. It is-
Alright, sorry.
This is not the Levi-Civita connection. This is called the Wiedenbach connection. Different name. So for that, in that connection, it is curvatureless. There is purely torsion. But if you, with that framework, if you calculate the Dicke square for the Riemannian case, then you will have this minus t, which is called the torsion scalar, which is defined through these definitions. And the important point is here that this Dicke scalar in Riemannian's space-time is equal to minus t, the torsion scalar, plus some total derivative. And so therefore, since total derivative do not appear in the field equation, so therefore if you take this gravitational action or Lagrangian, then that is completely equivalent to Einstein-Hilbert action. So that is called the teleparallel equivalent of GR. And modification, and if you take like in FR theory, if you take some function of t, the torsion scalar, then that is called the FT theory. And the field equation for this modified teleparallel theory is given by this, where G mu nu is the usual Einstein tensor, and d mu nu is defined by like this, theta mu nu is the energy momentum tensor. Now you see that this Ft is the derivative of F with respect to capital T. Tt is the 2 times derivative of F with respect to capital T. So if you take Ft equal to T plus some constant, then you get back the Einstein field equation. So that which is that means the teleparallel theory.
I may be missing some point. Your T
Yes.
is totally defined in terms of the torsion tensor.
Yes.
If the Lagrangian density is purely proportional to T, there are no time derivatives or space derivatives or any field. So when you vary the action, what do you vary with respect to?
This tetrad field.
Tetrad.
But
This-
nevertheless,
this-
it depends only on the symmetric part. T has no affine connection. So how do you get G mu nu in the equation? In LT, you get T. T depends on the symmetric part of gamma hat.
Here D also is there, also E is there, which is the determinant of G mu.
So it depends only on the frame. On the-
Yes.
So, but it does not depend upon the affine connection, just on the frame.
Yes.
Everything is tensorial. How does one get Einstein equations? That is this question I am asking again.
Now you vary this equation like T or F whatever with respect to the this tetrad field, and then after that you get this kind of equation directly, that you get this equation.
There is no other method.
also.
No, there is matter.
Matter is there.
Extra matter is
The previous one.
Here,
Yeah.
the
Because if you don't have G mu nu, then how are you going to get theta mu nu?
yeah, G mu nu is there. G mu nu is under root G mu nu. That is equal to E, the determinant
E
of
is
E.
there.
Yeah.
But, how do you get theta mu
no,
nu?
there is an extra matter coupling extra which is added.
Yeah,
Yes.
but how do you get theta mu nu from that? What do you vary to get theta mu nu?
You can write down means since G mu nu is related to the eta mu nu, you can get the same energy momentum tensor. If you vary the matter part with respect to the tetrad field also, you will get the same thing. You will get the same because in the matter part you have root mu G also. So, okay. Okay, and now the teleparallel version of the Born-Infeld is proposed by Fiorini in 2013 like this, where he have used the same Born-Infeld like structure, the square root structure, where F mu nu is defined like this, so that these constants C1, C2 and C3 they are related by this relation C1 plus C2 plus D C3. D is the dimension of the theory, equal to 1, so that the trace of this F mu nu that becomes the torsion scalar. So in that case, for lambda tending to infinity, the theory parameter, this action reduces to the teleparallel theory, teleparallel equivalent, and since teleparallel theory is equivalent to GR, so this action therefore for lambda tending to infinity, this action reduces to the GR. So now if you, the interesting thing is that if you take C1 and C2 equal to 0, this action reduces to like a FT-like form, and in 4th dimension, this FT have a form T plus T square by 4 lambda. So if you take lambda tending to infinity, FT becomes T. So that is the point. Now with this theory we have obtained some cosmological solution, and the Friedman equation, due to this FT theory T plus T square by 4 lambda, you have on the right hand side of the field equation, cosmological field equation, some geometrical contribution to the effective pressure and effective energy density. This is like a effective energy density and this is like effective pressure. But this is the geometrical contribution to that, and this is the to the effective energy density. This is the geometrical contribution to the effective pressure. And we have obtained some accelerating solutions. Even we have taken the dust field universe or some non-negative pressure. Even for that we have obtained some the accelerating solution. And we have also fitted with the supernova data, and we have seen the fitting is good, but some problem is there. The fit is good, but some properties of the universe like age, the deceleration parameter, time, present deceleration parameter, those things do not match quite. That is the problem. But except that this is the fit is good. Okay, now in this last 1 or 2 slides, I will just give you a glimpse of our current work, where we have done EIBI cosmology with scalar Born-Infeld matter. So we have taken like Born-Infeld electrodynamics, we have taken the scalar field in Born-Infeld like structure, that means the tachyon. So this is the V5, V is the tachyon potential, and we have used a parameter alpha t square like Born-Infeld electrodynamics, we have dp square. So like similarly we have used a alpha t square for the Born-Infeld scalar matter. And in our setup we have used a form. So usually people choose the form of the potential like exponential or anything that, but we have instead of that we have assumed the form of phi dot square for some definite reason. So we have that has been described here. I am not going to detail in that. This is the choice of our f dot square, and for that we have find some solution which connect to a early de Sitter stage of the universe, followed by preceded by the deceleration state, and at the end the dead time accelerating universe. So that kind of result we have got. So this is the plot of for that particular case. What is the scale factor? The scalar field, form of the scalar field with respect to time, and what is the form of potential for that. So this is the summary what I have told you, and my collaborators are Dr. Sandberg and Rajiv will say. So thank you.
Any questions?
Yes.
Is torsion an essential component in the framework of Born-Infeld gravity? Because
No,
in reduced case you got torsion.
Now, what is the motivation of this getting this thing? Is this question? What is the
I mean,
motivation?
okay, you have two type of matrix, right? And you have
That is a different framework. Here there is just only one. There, the two type of matrix was there because their metric and connection was different, independent. So due to that connection, different independent connection, we have a different metric which we call the auxiliary metric. But here there is no such thing. There is a single variable which is stated. So therefore the physical metric, there is no other. There is only one metric. Yes.
Can you oh sorry.
That's all.
Tell me.
Go to the next slide, but I think there is some.
This one?
Yeah. So here, suppose you take a very simple case where your trace of, I mean, the t which you write at the last term. Suppose you write it as some scalar field. You can do that by just choosing your t mu nu alpha as some axiom of field.
But here T is a torsion.
Yes, but you can write it in 4 dimensions as a dual. I mean, the 3 tensor t. You can write it as a dual of a scalar field.
It's not totally anticipated.
I'm going to a simple case where it's just totally anticipated.
Special case it can be.
So then you are generating through that Lagrangian some theory which is again some higher derivatives scalar theory. Can it be interesting in some sense? Can it be related to some usual scalar like Galilean theories?
I have to see. Okay, thank you for the.
And secondly, in some previous solutions, you mentioned some wormhole.
Yes, yes.
So there in the expansion, you say expansion stops somewhere, right? It's zero somewhere. In some.
Yes, yes.
So there must be some vorticity effect effectively coming from those Born-Infeld like terms.
Rajibul can.
That expansion is for ingoing non-zero. For that omega is
Vorticity is zero.
even shear is zero.
Even shear is zero.
So my question was also about this Lorentzian wormhole. Since the throat of the wormhole is proportional to the kappa, the constant, so if you want to have a macroscopic wormhole, then you require a certain value of kappa. But also from other experimental tests, I don't know what is the constraint, what are the upper bounds.
Yes,
on
there is upper bounds on kappa.
In that paper, to try to find out the tidal force for an observer which is traversing the worm. So we found that if we restrict the tidal force to less than 1 Earth gravity, that there is some restriction on kappa, both on kappa and both on wormhole throat. And the minimum wormhole throat that we found is 8.6 times the Earth rate.
Okay. And how does it correspond to the observational constant from other?
For the observational constant, so that one was calculated by restricting the radial component of the tidal force to 0 on Earth gravity. But there is some solar constant on kappa. So if you use that kappa, then we found that the minimum radial component of this tidal force is 17 g. So So if you use that, then you can say that from that you can calculate the minimum radius for the Born-Infeld protest. That will be around 9 or 10 times the radius minimum.
Okay, so if there is no other question, let us thank the speaker. And we break for tea.